Okay, thanks for having me. I think of Sparse Days as kind of my community. I have fond memories of the first meeting in Sancharan, and my goal today is to sort of review a familiar problem and introduce the work of my IDA colleague, Miller Maley, um, uh, who trying to introduce him to this community. He lives in a parallel universe of shared memory programming. Um, like Newton, we're standing on the shoulders of lots of giants, some of whom are familiar to this community as well. So brief outline, a little bit of motivation, which should be familiar to everybody here. Basically, sparse matrices lead to sparse communication patterns. Small messages that might naturally come out of that perform poorly. I'll review a couple of the strategies for dealing with that I think probably everybody here is familiar with, and then introduce, using that for contrast, introduce conveyors. So communication, I think, is ubiquitous. In my solver, the user can supply columns arbitrarily distributed amongst processors. If I want to call Parmetus, I have to change that, and then Parmetus itself splits the graph, so it has to redistribute the graph as it proceeds. Let's see, I'll show an illustration of that in a second. Symbolic analysis has a different distribution. You want to redistribute the matrices before you actually factor. This is sort of one-time work if you're in something like a Lanczos eigensolver. Within the multi-frontal factorization or the triangular solves, you've got to gather and scatter up and down the elimination tree. So sparse communication is all over the place. This illustrates the problem for reordering. If I have a little 3x3 grid, where that's the graph of my matrix, I have 5 processors, then I have to call Parmetus, I have to group adjacent columns together. For my symbolic analysis, I like to distribute the graph in chevrons, as illustrated here. So not only is the permutation different, but the distribution to processors is different, right? And I don't want to illustrate all the others because time is short. And here's some data from Miller, basically illustrating what we've all experienced, that if you send small messages, so the gray bar on the left, if you have an 8-byte or 1-word message, then it's 38 times slower in terms of effective bandwidth than a message of effectively 1,000 words. So we're all familiar with this, whether you're putting or getting, you need to have a reasonably big message in order to, get effective bandwidth on today's systems. Okay, so how might you go about aggregating messages so you're sending thousands instead of individuals or small tuples, say? So one thing you might do is say, well, in MPI, there is all-to-all and all-to-all V, right? So I can traverse my subset of the matrix. I can look at every coefficient, decide who it's going to, accumulate counts. Then I can do an MPI all-to-all, and we'll exchange the counts, and now I have a vector receive count that tells me how many messages I'm going to receive from everybody. And I, of course, send count, which tells me how I'm going to send everybody. I can compute displacers and allocate send and receive buffers. And then I can do an all-to-all V. Everybody now has all their data, and they can unpack tuples from the receive buffers. One issue here is that you have to create the send buffers and you have to create the receive buffers, so you're allocating memory. So now instead of, I've got an initial value of the initial copy of the matrix that my user created, and 3 of my own internal ones, the send and receive buffers, and then the final permuted matrix. So you can overlap the send buffer with the permuted matrix if you're clever. So maybe you only have the equivalent of 3 copies of the matrix, but still there's some additional storage. And it's a big bulk synchronous MPI operation. So pretty quickly, I think everybody I know who's been down this path decides, well, they could save memory if they just had small buffers and reused them. And so then you discover MPI asynchronous communication. So just an outline of how you might do that is initialize receive buffers for, all the other processors, or post-receive buffers, I should say. Now traverse the matrix one time instead of twice. In this case, I'll look at each coefficient, decide who needs it. If it's not one of mine, I'll try and put it in a send buffer. If it's not available, I'll wait to receive something and loop until it's all done. Then I have to flush my send buffers, wait for any receive buffers that are still pending, and then wait for the last of my send buffers to complete. So I'm going to walk through this in a little bit of detail just to show you how ugly it can get. So I have to initialize the send buffers or receive buffers, so I'll loop over all the processors. If it's not me, I'll call MPI I received to post a buffer. Then here's the most fun part. Now I loop over, my columns of the matrix, loop over each value within a column. That's the do I equal JK loop. Decide whether the permutation of R is bigger or smaller than the permutation of C. I can decide which processor owns the resulting target. If it's me, I can just save it away. I'm done. Otherwise, I have to see, is the send buffer available for me? If it's not, then I jump to top right where I have to wait for something, like maybe my send buffer to free up. But when I wait, I might get I might receive instead. And so if I receive, then I unpack what the buffer I received. And if that guy's not done with me, I post another receive buffer for him. If I'm lucky, then I have the else case where I can pack up my tuple. And if my buffer is full, I do an MPI send. So, it's a complicated thing, and you try and get rid of, make this MPI wait any more efficient by adding another layer of buffering for the messages that, can't be sent, but that would make it even more complicated. I have to flush my send buffers when I've traversed the matrix. So that essentially I have the same construct where I have to watch out for the case where my send buffer, a previous send buffer hasn't been finished, and do a wait. I have to pick up all the outstanding receives and then wait for the last of the sends to complete. So a lot of code. It can, easily grow to hundreds or thousands of lines. And so I think everybody in this call, I guess I'll call it, has probably done something similar. So my friends at IDA sort of went down this path as well. In the good old days, they had a parallel distributed shared memory programming model on Cray T3Es. They used unified parallel C and SHMEM. And as one of my colleagues likes to say, we were happy. Of course, you can't buy a machine like that today, so they've moved to shared memory programming on clusters instead of distributed memory. The net result is they've started rediscovering things like MPI all reduce. They call it UPC all reduce. And one colleague in particular then repeated my journey. First, he had a UPC collectives-based version, then an asynchronous version. And this inspired then Miller-Maley to invent a new abstraction called Conveyors and build a library for it. He built his library in C, and Bill Carlson is, we are stuck home because of the pandemic, so Bill Carlson implemented a version in Rust. So here's the API. It's really, really simple. Basically, there are two collectives. One is begin, that's equivalent of MPI init, and then there's one to reset it. And then instead of having send and iSend and all the other variants of send that MPI has, they just have a simple push if you want to send something, and pull. So push, I just need to have an object, whatever it is, maybe a tuple in my case, and I need to know who it's going to, and pull returns an object and the source. And then I can advance the conveyor, which is the equivalent of sort of flushing all the buffers, right? And that's it. That's the whole programming abstraction that you need. All of the details of managing send buffers and communicating them and receiving them, all of that is buried inside of the library, and the user doesn't have to think about it. Just like in an MPI all reduce, there are probably half a dozen PhD theses on how to optimize that for different sizes. We don't have to worry about how to do that. So this is what that looks like. Now, I made a fake version of this because the original conveyors didn't work on top of native MPI because, again, Miller came from a shared memory world. So I made a fake version. This is what the same structure looks like. You walk over the matrix, you get down to where you have to communicate, and now I just say push. and if I can't push, then I pull until I run out of things to pull, and then I try and push again. And so, it's a simple, tiny abstraction. Um, in the end, if you want to flush your send buffers, you just call advance, and then pull until you run out of things to receive. So much simpler than before. Miller made a high performance implementation of this. So he's got the first version was made with what I'll call simple conveyors. It's basically I send and I receive, as I described earlier. Then he made a second, more sophisticated multi-hop version. It's similar to what's in You've Got Mail, but it was also similar to work that IBM and Sandia did for winning the random access benchmark competition. And with the multi-hop things, now the buffer size is not scaling linearly with number of processors, but is rather sort of bounded and small. And the message size, the library auto-tunes that, so you don't have to figure it out for yourself. So this illustrates again the here with more detail Miller's data from before. So now you see the delivered bandwidth of the packets, which is the violet part in the bottom, and then the blue and the pink parts are the overheads for addressing and routing tags, which you see are pretty small and diminish as the object sizes grow. So this is sustained bandwidth on a oh shoot, I can't remember the name. One of the Cray machine, maybe 2 or 3 years old. So that's pretty significant, a pretty substantial fraction of peak. And the packets he's sending are roughly a gigaword in size, a little bit under a gigaword. This shows the difference in performance between the sort of simple conveyors, the Fortran ones I sort of showed, versus the multi-hop ones. The multi-hop ones are consistently faster by about 25-30% than the simple point-to-point sort of I send I receive versions. And the good news is the tensor conveyors are there's a high quality implementation that's available on GitHub. So just to summarize, so everyone can call today. I think conveyors provide a convenient abstraction for message abstraction. They would certainly improve coding performance or programmer productivity. Unless you're very sophisticated, they would improve the code performance as well. Again, there's a high performance open source implementation on GitHub. Goes to Jason Deviney's Bail directory. It can run on top of UPC and Shmem, which was the original environment it lived in. And Miller now has it running on top of native MPI as well. So you don't have to run these independent of your MPI applications. And the good news is it's ongoing research, so it's only going to get better. Anyway, with that said, I'll quit here.
All right. Well, thank you, Bob. You can hear the rousing applause from the audience. So lots of discussion on the chat. In fact, I don't think I can get to all of it. So you should look it up later. But a few questions here. Let's see. Do you need, for the MPI side, do you need one-sided MPI support to do this?
I don't believe the implementation. I have no idea how he implemented it. And what I showed you did not have MPI one-sided communication. I was just using the original asynchronous stuff. Okay. So certainly you could implement it with one-sided communication, and just that's certainly possible.